Okay, welcome everyone to another exciting video lecture. We're going to discuss today chapter 12 in your textbook, and we're going to begin a little bit with chapter 13 as well. I first want to state some ways. By the way, chapter 12 is about solids and chapter 13 is about liquids. I want to state some ways in which we can think about both of these forms of matter in similar ways. So first we're going to look at a couple properties that are common to both solids and liquids, mainly density and pressure. So density is going to depend upon what your mass is per volume. So it won't matter how much of the substance you actually have, it will just matter how much of it is packed into each volume. Typically, solids are going to be more dense than liquids, but there are some exceptions to this. For example, ice is actually less dense than liquid water, otherwise your ice cubes would sink in your glass rather than float. And floating and sinking we'll get to probably in the next lecture. Anyway, mathematically speaking, then how to determine the density is just going to be taking the mass of your substance and dividing by volume. So the units involved then are going to be kilograms per cubic meter. You may also see some other conventions that are not SI units, such as grams per cubic centimeter, and so on. The other property that I just mentioned, pressure, is mathematically the equation you need is basically the force divided by the area. So it depends not only on the force, but how the force is distributed across an area. The SI unit for that then is going to be a unit of force, the Newton, divided by unit of area, meter squared, and then we call that a Pascal. Okay. So some everyday examples you can think about. The bed of nails. If you were to just stand on a nail, it would puncture your foot, but for some reason you can lie on a bed of nails. Why should that be? Well, because you're spreading the force, in this case the weight of your body, across a greater surface area. And so the pressure on your skin is actually tolerable instead of being able to puncture your skin. Another example I like to point out is if I were to stomp on your foot with a regular shoe, that might hurt, but if I were to stomp on your foot with a heel, a stiletto heel, that would hurt more because I'd be applying the same force to a smaller area, causing greater pressure onto your foot. Okay, so along those lines, here's a clicker question we would do in class if we were discussing these things in person, but you can think about it and pause the video if you like. The question is, if you were to stand on one foot instead of two, how does the force you exert on the floor compare? The answer is that the force is the same. You're still weighing the same no matter what. You haven't suddenly lost weight just by virtue of standing on one foot instead of two. However, the pressure on the floor is going to be more because you are applying that whole force of your weight to a smaller area, the footprint of one foot rather than of two. Okay, so that's a little bit of an intro to density and pressure. Like I said, these concepts apply to both solids and liquids. Now I want to delve into chapter 12 and get going on properties of just solids. And then towards the end of this lecture, we will go into some, at least the first property as it applies to liquid that is presented in chapter 13. So properties of solid that we're going to discuss, some of these more briefly than others. One thing is that solids often form a crystal structure. As we're going to see in a minute, that's not always true. Different molecular bonds are possible in solids, and those determine some properties about the solids. And then we're also going to look at how solids can stretch or compress. So along the lines of crystal structure, if you look at how the atoms are arranged in a solid, oftentimes they form some regular pattern that we call a crystal in nature. But not all solids do this. There are some that are amorphous and have less regular shapes to them in terms of their arrangement of their atoms. Speaking of atoms, the way in which atoms bond to form molecules can take on different types of bonds in a solid, and these can determine what other properties the solid has. Unfortunately, we don't have time to go into all of these in detail, and your book really doesn't handle this either. But the 4 different types of bonds that you can keep in mind are ionic, covalent, metallic, and van der Waals. We again aren't going to really discuss how that determines some of the properties of your solid, but one example that you can think of automatically is the metallic bond. In a metallic bond, the electrons are more loosely bound, and so when that happens, it's easier to get them moving through the substance, which is why substances that have metallic bonds tend to be good conductors of electricity, because electricity is nothing more than the flow of electrons through the substance. Okay, so then getting to the heart of the matter, really what the emphasis is in Chapter 12 is on the way in which solids can stretch or compress. And so we're going to explore these concepts in terms of tension and compression. So the example that you're seeing here is something heavy placed on a girder. And when that sort of bowing occurs that you're seeing here, obviously this is sort of exaggerated so that we can see it. What you can think about is that throughout this girder you have different things happening. If you look at the top layer, it's being compressed as this U shape is being formed, whereas the bottom layer is being stretched, so it's under tension at the bottom. So you may have seen this if you have some cheap particle board bookshelf and you place some heavy books in it, that over time it takes on this sort of bowing effect, and then the top of this shelf is subjected to compression and the bottom of this shelf is subjected to tension or stretching. Of course, it matters where you place a heavy object. If you place it, say, on the end, like this, such as maybe on a diving board, if you're standing on the end of it, then it's the top that is being stretched or under tension, and the bottom that is being compressed. So basically, if you're forming a U shape, then whether it's a smiley face or a frowny face, whatever's on the inside is what's being compressed. So right here is being compressed, or right here is being compressed. Whatever's on the outside is under tension or being stretched. Okay. Now, if you think about it in 3 dimensions, then here's a thought experiment for you. I'm not sure why you'd want to do this, but suppose you were to drill a set of 3 holes through a tree branch as indicated here. The question is, where will the tree branch remain the strongest? So go ahead and pause the video if you want to think about this clicker question, but I'm just going to direct you back to this cartoon here where you can see that there is tension happening here. Whoops, I meant to go backwards. Tension happening here, compression happening here, and along the dotted line you see less of either of those. So that's why the answer to this clicker question is that near the middle you will not, you will have the strongest part of this tree branch, because it is under less stress when it comes to tension or compression. It's more intermediate. Okay, and so that gives us a justification for why in construction I-beams are a popular design. For an I-beam, there is reinforcement on the top where perhaps there might be tension or compression depending on where you place the weight. and the bottom that also may be under tension or compression. But we don't need as much reinforcement in the middle because the middle is going to be subjected to less tension and less compression. And so by making this part thinner, we save ourselves some cost of materials, we save ourselves some weight so that we can move these I-beams around more easily. And so this is a very favorable design in construction. So to quantify this further, we really need to talk about Hooke's law. Now, Hooke's law, as it's typically discussed, is how it applies to springs, but this idea can actually be generalized to solids in terms of the length change that occurs during compression or during tension. Basically, Hooke's law tells us that the force that we apply, that the extension or compression that we see is going to be proportional to the force that we apply. And so the more force we apply, the more this thing will extend. And depending on the material, or in this case the spring in this example, it may be more or less easy to achieve that tension, that extension or compression, but for whatever given spring I have, the more force I apply, the more I expect to see the extension continue or the compression continue. So, for example, let's suppose that we have a spring which is originally in its relaxed position 10 centimeters long, and when I stick a 1 kilogram load onto it, I see that it extends to 12 centimeters. So the question now is, what will happen if I add a 3 kilogram load instead of a 1 kilogram load? So you can pause the video if you like. And the answer to that is, well, I'm applying 3 times the force, right? So I expect 3 times the extension. Now remember that we're talking about the extension. We're not talking about the original length of the spring. So it's not as though I can say, oh, well, it's 3 times the 10 centimeters. No, it's 3 times the extension that occurred with this 1 kilogram. And the extension was 12 minus the 10, which is 2 centimeters. Okay, so now I expect there to be 3 times that extension. So 3 times the 2 centimeters should give me 6 centimeters of extension, which I add on to the original 10 centimeter length to come up with this value here, 16 centimeters. Okay, so I'm mentioning Hooke's law, and I'm saying that it can be generalized to solids in terms of their stretching and compressing. And so here's a visual for you that sort of conceptually shows that. If I have some solid here and I'm able to apply a force, then the amount of extension I see should be proportional to the force that I apply. And of course it can work in reverse as well. If the solid was originally this length and I'm able to apply a force to compress it down to this length, then the the amount of compression will be proportional to the force that I apply. It's important to note that Hooke's law is what we would call an approximate law. It's not always going to be the case. There will be a point at which you can actually break something. As you probably know from your own experience, too much stretching can actually break something. But for small extensions and compressions, it's a reasonable approximation. And as I said before, though, the exact amount that you're able to extend or compress something will depend upon the substance itself. And that's another reason that steel is a favored material for many types of construction, is that constant of proportionality is fairly large for steel, so it is less susceptible to being stretched or compressed than weaker materials may be. Okay, so that about wraps up Chapter 12. I want to introduce Chapter 13 in terms of some of the concepts that are unique to liquids. I've already introduced the idea of pressure. Now we want to explore pressure as it applies to liquids a little bit further. In the next lecture, we will also look at buoyancy in liquids and flow of liquids. So the pressure in a liquid is still defined as the force per area, just as we discussed earlier. And the area could be your entire surface area. So if I'm submerged in water, I will feel the pressure all around the surface area of my body. But the thing that's interesting about liquids is that this is also a depth-dependent quantity. It doesn't matter how much of the fluid is there, but it does matter how deep I go in it. You've probably, if you've if you've gone swimming in a pool of any depth, you probably had the experience of feeling more pressure on your body as you go deeper and deeper into the pool of water. And so that's like a general property of pressure as it applies to a liquid, is that it really doesn't matter how much or the shape of the container. What matters is how deep you are. So in equation form, it says in your book, the liquid pressure is going to equal the weight density times the depth. What does that actually mean? So in variables, I would call this pressure P. Now, weight density, what does that mean? Well, we've already discussed what density is in general. It's mass per volume. But to turn this into a weight density, I just need to multiply by little g because mg is my weight. Okay, and then I can multiply that times my depth. So notice that we said that the density of something doesn't matter how much of it, it's just how much is compacted into per volume, per unit volume. And so the same idea is true here, that how much of it I have doesn't really matter. But for example, fresh water's density is different from salt water's density. Salt water's density is less, and so I would put a different value in here for my weight density for salt water than I would for fresh water. And so I would then conclude that the pressure on my body, the depth at which I am diving, will be, perhaps I can go a little deeper in salt water than I can in fresh water for the same amount of pressure. So again, this pressure is acting on all surfaces because it's acting on your entire area of whatever object, such as your body or an ice cube or what have you, is immersed in the water. But what really matters is how deep you go. And so you can verify this, and feel free to try this at home if you are bored with being stuck at home. You can fill a paper cup with water, and you can puncture it at different heights, and you will see that the more pressure that occurs here lower down in the container will cause the water to shoot out at greater speed because it's under more pressure than the hole, than where this hole is, where it's near the top. Okay, and this also goes into the shape of water towers. Because it's the depth that matters, you have often these thinner parts to the water tower here, and then the more of the volume on top, and that is because the taller that we make this, the more water pressure we can achieve here at the bottom because it's at a deeper level, and so the actual amount doesn't matter, but how deep I am matters, and so I can get more pressure here for the same amount of volume. All right, and that's where we'll stop with this lecture. We will continue discussing liquids in the next lecture. We'll talk about buoyancy and flow of liquids, and I will talk to you again then.